Well, shall we get started? It's 5 after. Those who want to show up, I guess, are here. So thank you all for coming out on this Sunday afternoon, allowing me to abuse you a little bit with hopefully a little useful information here. For those of you who weren't here the first time, my name is Terry Panhorst. I'm a retired geology professor. I also worked in the mining industry for over a decade, so I've kind of been around, kicking around the western United States now and again. And Randy and I have kind of conspired to sort of try to put together some training sessions for volunteers, and in particular the education group or committee, is it? So that you all can get the sort of information that you need in order to answer most questions. Now, you know, what we're going to do today is not, I mean, you're not going to have all the information, you're not going to have all the knowledge or anything. Nobody really has all that. But it should hopefully give you enough background that you'll feel comfortable no matter what the audience is. Obviously, answering the question of a third grader is a lot different than answering a question of an adult, although sometimes there's a lot of similarities. But so anyway, as we go along, if you've got questions on things, please don't hesitate to ask. This is going to be a little bit of free form as we go along, and I assume that I can go till 6, right? Wasn't that the agreement? Okay, so you suckers. Okay, anyway, what I'm going to do today, like before, is approach this with the idea that you all have very little to no geologic background. Those of you who do, I know, I apologize, but we'll just try to get a bunch of terms down that are used consistently in this whole process. So that'll be the sort of the front part of what I'm talking about today, and then we'll get into the development of the Western Snake River Plain and at least some theories on how this whole thing operates or has operated. So to start with, let's just do a little sort of background on a term that we all use, a fault or faults. In a geologic definition of that, I think it's pretty functional. First of all, they're discontinuities in rock. Now, by discontinuities, I mean they are essentially a fracture in the rock. And because of this fracture with a fault, you're going to get a mismatch of geologic features from one side of the discontinuity to the other. Now, all rock masses have what are called joints in them. Those are just straight fractures. And okay, well, I can follow this contact along, I hit the joint, and then I can follow it exactly the same elevation or same place on this side. Okay? So there's been no movement across that discontinuity. So that's not a fault. The fault is when we get movement, all right, and a dislocation, a mismatch from one side to the other. That's the critical evidence for that kind of feature. Now, the fault planes themselves, despite our desires otherwise, the fault planes themselves are actually very rarely exposed at the surface. And the reason for this is because they are a zone of weakness. They're a zone of fracture. Rocks tend to get busted up along those things. And so they're very easy to erode. And so if you look at most typical geologic maps, and they'll show a bunch of faults on there, commonly you'll also notice, if you've got the topography on that map, that the faults line up with where some of the valleys are, because that was easy to erode. And so over the years, that is what eroded. And so we can't actually see the fault, but this hillside has different rocks than this other hillside, and we can't explain it other than saying, well, there must be a fault through here to cause that mismatch. So we're not actually seeing the fault, but there's evidence of it. In fact, I was thinking sometime in the future here, I should probably give a talk on fault zone structures, where you actually can see the fault and all the different interesting features that develop out of that. Okay, so what we really focus on here is the results of the faulting. That's when these faults are detectable, and that's when we identify sort of them in their location, or at least try to approximate that. Okay, some terminology for fault walls. One side versus the other side of the fault. They're important because that determines what kind of fault it is. So we're going to use this simple little diagram. And on the left side of this diagram, we have what's called the hanging wall. Okay, so if you're underground and it's the block that's over your head, it's hanging over your head. So that's considered to be the hanging wall. On this diagram, that's the left side. Okay, what you're standing on is called the footwall, because that's what you're planted on. So hanging wall, footwall. Simple concepts, but it's important because the direction that the hanging wall moves relative to the footwall is what defines the different types or different names we apply to certain faults. Okay, so we can have what are called normal faults. In normal faults, the hanging wall block, shown here on the right, always goes down relative to the footwall. Now, does it always go, is it really going down? Well, we don't know. Maybe actually the footwall went up. But all we know is, relative speaking, the hanging wall is down relative to the footwall. So that's a normal fault. You get that frequently when you pull things apart, an extension. And we have a tremendous number of normal faults throughout the whole western United States. Those are the big players, really, in a sense, the most common ones. We have them all over the place. There's some, right around us here. You could throw a rock and hit one actually right out here, or at least get close to it anyway. Okay, now here's an example in an excavation that I was working at, where we do have a nice example of a normal fault surface. And that surface is right here, kind of comes down like this, approximately. Now, first of all, note that if you were just walking across the top of this thing before the excavation, you really wouldn't know where that fault was. You might know that there is a fault there, but you wouldn't know the exact location of it. And a good indicator of the fact this is a normal fault is you get this phenomenon called drag here. Okay, and it has nothing to do with, dressing up. Okay, drag is the result of when you have, say, a fault surface and you have a bed that's cut by the fault, and when the block moves down, in this case the hanging wall moves down, it kind of pulls it down so that, maybe I'll do it like this, so that it sort of sticks close to the fault. And so you have this seeming curvature that points sort of back up that way. So that's what's referred to as drag, and that's a pretty good indication that this block has moved down relative to that block. Yes?
Okay, so the block went down, but you said the curvature, so there's like...
The curvature of this unit right here kind of works its way up like that.
So between your two arrows, is that just kind of where it's stretched, or?
No, this continues on up to the fault surface,
okay,
which is approximately right there.
Oh, okay, I got it.
Okay.
Yeah, that was kind of...
Yeah. Now, where this is on this side, you can't really tell, which means there's probably been a significant amount of movement on this fault.
It would be like in stages too, if it...
Oh yeah, yeah. It doesn't typically all happen at once. Yeah, but wherever this is on that side, that may have already been eroded off. But we do see it over here. So that's part of that mismatch. I'm walking along here, I'm in this junk here, and all of a sudden, boom, I hit that. That's a mismatch. So that's, okay, I'm going to look at that. Okay. On recent faulting, you can actually see the scarp. In this case, this is the Fairview Peak, Nevada earthquake, which was like just slightly over a 7 magnitude. in what, 54? And this is the scarp right along here. But even after that, that photo was from approximately 1993. Okay, so 30-ish years, 40-ish years between when the thing actually formed and when we were out there looking at it. And you can already see that that scarp is beginning to degrade. They go away pretty quickly, actually, unfortunately, but they do. Okay, so that's an example. A little one closer to home here is Mount Bora. Classic. You all have probably seen this photo, you know, with the fence on here. Excellent example of that situation. There's that fault scarp. And over time, that will degrade away. But there we know exactly where the fault occurred. Of course, it wasn't too difficult to tell because you're out there right at the time or shortly thereafter. Okay, something that's a little bit harder to tell here is this fault is, the thinking is it's maybe about 2,000 years old. Now, we've got kind of a rise right here. It's almost like a little hump in this area and then a flat basin over here. Okay, so this fault scarp has been degraded pretty well, but the fault probably is somewhere right along over here. And typically that's where it would be mapped. The assumption is that this is a normal situation because this is our basin here. This side moved down, and so it probably reflects something of that nature, you know, kind of close to where you get that change in slope as one walks across the thing. So kind of subtle, but nonetheless, physical evidence. Yeah?
Maybe I missed the definition of a scarp. Is that where the fault, is that the fault line?
The scarp, let me go back. The scarp is this thing, this slope right here that's exposed at the surface. And if you go, let me go all the way back, that would be the scarp right there. So if you're really lucky, which typically doesn't happen, but if you're really lucky, you can get out there right away and you can actually see the polished surface of the fault itself. In these cases, that wasn't the situation. Okay. Whoop, I'm going backwards. Sorry. Let's move on ahead here. All right. Whoop, I did get too far ahead. Okay. Now, reverse fault. We talked about normal faults. The opposite of that is the reverse fault. Reverse fault is a situation where the hanging wall moves up relative to the footwall. Typically in what's called a compression situation, so you're pushing things together. You have compression, you have extension, or horizontal motions in that fashion. So the hanging wall moves up, and that's the relative sequence that one might see. Less likely to get a scarp, although you can. It's just a lot of times less likely. An example of that, there's our fault right there. And one can tell the motion direction because look at this series of beds here, same series of beds right here. Okay. Back in time, obviously that would have continued all the way across. Snap, the fault occurs, that moves up in that direction. So a reverse fault. Less common, particularly in this area, but nonetheless it does occur. Okay, the third category I'm going to talk about are what are called strike slip faults. And this one is probably the most familiar to you just because most of the big faults we worry about are strike slip faults. In that case, you don't really have a hanging wall or a footwall. Most strike slip faults actually have nearly vertical fault plane. And so if it's vertical, which one's hanging over the other one, you can't tell. The motion now isn't so much vertical, it isn't one up over the other or something like that. It's side-by-side motion. So in this case, we have stress being applied in that direction, give it a push that way, which is going to cause a push in that way back there. And so that's the relative motion that one would get with a strike slip. Okay. San Andreas is the classic example of a strike slip, at least in North America, that we know most about. That's actually much more of a fault zone. I'll get to that here in just a little bit. An example near Vegas, where you've got a series of beds right here. On this side of the fault, they're now over here. So the main types of strike slip, you have right lateral and left lateral. So the way you determine that is you stand right at the fault. Okay, here's an object, maybe a bed that I'm standing on, and I look across the fault. Okay, where is this bed continued across the fault? If it's over there, it's a right lateral fault. If it's over there, it's a left lateral fault. And what's really neat is it doesn't matter which side of the fault you stand on. If I stand over here, I get the same relationship. Okay, so that's kind of handy. Okay, now San Andreas, like most fault zones, when you really get to look at them in detail, aren't a single surface. In fact, they are better described as fault zones because you have a whole sequence, kind of a tabular region many times, that has a whole sequence of faults with individual blocks in between those individual strands. So it's a far more complex kind of thing. This area too frequently gets ground up, and it's very difficult sometimes to interpret that. So we know there's a fault zone in here. It's just that it's exactly what's going on. It's really hard. So that's the time when you like to put drill holes in it or have an excavation across it or something like that. Highways have done amazing exposures for us, particularly in Southern California, where you blow a highway through a ridge. I used to drive by this every day, where the San Andreas is exposed. And yeah, it's wide. It's 3 times the width of this room, and the beds in there are just all convoluted, churned up and stuff. And it's complicated, to say the least. But it's very interesting too, unless you're driving and then you run off the road. But my wife was always fussing at me about doing that. I mean, come on. Anyway, another topic I wanted to go into a little bit is how we represent faults on maps, because that's probably the way you're going to see most faults, particularly when you get out into the museum or looking at geologic maps on your own. And there's kind of a standard sequence that's used. Little variations, but there's a standard sequence that's used. First of all, if a fault is very well located, maybe we can see it in an outcrop, for instance. We know it's here, it's real obvious. Then it's shown as a straight line, solid straight line. Okay? In this case, it also has a designation which tells us the dip direction. Now, I'm going to let me specify a couple things here. First of all, this long line that I've got there is what's referred to as the strike of a fault. Let me borrow this. Big but effective. Okay, a strike is basically, in the simplest definition of the strike, it's the intersection of 2 planes. The intersection of 2 planes forms a line, right? Basic geometry kinds of things. All right, so if I have a dipping plane and I bring a horizontal plane into it, the Earth's surface, the orientation that line has is what I refer to as the strike. And because this is in map view, I can give it a numeric orientation. This one's about, say, 45 degrees east of north. Okay, so you can express it in there's a standard nomenclature that's used for that. North, 45 degrees east, or if you're working in the other system, the azimuth system, which doesn't use letters, it only uses numbers, it would be a 045 degree orientation. Okay, so we can give that an orientation. And to receive that on a geologic map, there darn well better have been somebody out there that saw this surface that you could actually put your Brunton compass on and measure this sucker. Okay, and that's your best positive evidence of it. Okay, that's the strike. Whoop, I still need this. Okay, the other thing that's important here is what's referred to as the dip, both the amount of and the direction. Now the true dip is always measured perpendicular to the strike. So I have a strike here, and if it's sitting like this, that's the dip direction. The dip amount is measured down from horizontal to the surface. So in this case, maybe that's like that one, that would be a 65-degree angle down. All right? So again, you have to have excellent exposure in order to determine that. But that's the smoking gun we're always looking for. Okay, we got a good idea on what the dip amount is going to be. And you can see this frequently on maps. Okay, that's when a fault is well located. Okay, if a fault is approximately located, a dashed line is used. Sometimes they use longer dashes, sometimes it's a little bit shorter dashes, but line. So there there must be a fault. There's a mismatch here, but I don't know in between where the fault actually is. Based on my understanding, my knowledge base, I'm going to say it's about here. Okay, approximately located. Frequently, they are then marked, either side of the fault, U being up, D being down. If I know the dip direction, then I could label this. Oh, well, if it's dipping in that direction, maybe that would make this a what kind of fault? Yeah, if this side moved down and the fault is dipping in that direction, is that a reverse fault or a normal fault? Normal fault, yeah. Okay. Hanging walls move down, foot walls moved up. So if I can tell that, I can go ahead and label that. Now on a number of maps, they don't use that UD system. That's actually, from my experience, a little bit more modern invention. Yeah, I've been around a little bit, shall we say. So modern is a relative term. Okay, a lot of the maps have this ball and bar symbol, where the ball and bar are always put on the down dropped block. So if I don't have a U and D, if I see that, then I'll know, okay, that side's gone down, this side's gone up, relatively speaking. Okay, everybody with me? All right, good. Nobody's snoring yet, so that's a good sign. Okay, if a fault is assumed, but I'm not really sure where it is, I'm really uncertain on its existence, then you use, even shorter dashes. It's about here. Sometimes those faults are put in, not so much in the field, but that night in the bar. It's like, it's got to be here somewhere. Depends on how many beers you've had prior to marking on the map. But, that's the way it works out sometimes. Okay, if a fault is concealed by younger materials, then typically you use a dotted line. Now, I was working in PowerPoint, and PowerPoint doesn't seem to like dotted lines, so they just have tiny little squares. But pretend those are little circles. A dotted line. Yeah. It's going to be, I have a reasonably good idea that this is where this fault is. I'm assuming it's here, and it's got to go from here to here, so I'm just going to put it through here because we've got all this alluvium on top, and I can't really see where it is. Okay. Let's look a local map, shall we say. Okay, look something familiar. Okay, let's see, where are we going here? Well, you got Chinden on here, you got State Street, downtown Boise's in the area. You can see all that. Okay, for reference, the museum sits about right there, approximately. Okay, so what are we looking at here? What do we got? Well, there, it's marked as a pretty darn well-exposed, well-established fault. And then as you go southeast of that, it turns into dashes. So what does that mean? Well, maybe you've got topographic evidence that that's where the fault would go. You can tell the change in rock type here, which side's up and which side's down. Easy enough. Okay, foothills faults right over here, this one, right outside our door, so to speak. Okay, well established. Now, how could that be well established? Because there's no fault surface exposed over there. Yeah, but we do have those geothermal wells. Yeah, in that side out there. You drill down with that, you've got data up on the hill and you've got the data from the wells. Okay, yeah, we know it's there. Well, now you get away from that and all of a sudden, I don't know exactly where it is, but it's all covered. So dotted is an appropriate one. Okay, one of more speculative sort of location is this Eagle West Boise fault. Comes winging in right here and kind of comes down here and sort of, well, I don't know what to do with it, so we're just going to leave it there. We just stop. Okay, up thrown, down thrown, pretty well established. That's pretty good. But exactly where it is, that's all covered stuff. We can't see it. But it's reasonable to assume that it's probably about in that location. Okay, questions about that? Everybody sort of see the process? Yeah.
So the fact that this East Boise fault goes through the Boise River, does that tell us that the river came after the fault? Or can you tell?
Well, you can't directly tell, but it would probably be very reasonable that the location of the channel may well follow the same trend as the fault does and be close to it. Now you got to realize that there's a whole bunch of sediment between where the river is and where a fault was probably exposed there, and so we don't really know. You know, that's a bit of a barrier that we don't know how soon or how long ago the fault last moved. You know, and so if it's been a long time, then you've got a lot of sediment built on top of that. And so the fact that the river is coincident with the fault in certain areas, that might just be coincidence. Yeah. Yeah.
There's a terrace line right there around Shinden, and
Yeah.
the River's been doing its thing. And
Mm-hmm.
so, and that was Lake Idaho sediment everywhere. How do you know there's a fault there? I mean, do you drill holes to see it, or is it?
Well, that's part of it. You just look at the evidence of drilling that's been done in the area, and you also there's been seismic information. I'll get into that a little bit of that here. Various geophysical methods can also give you an indication that it's probably reasonable to assume that there's a fault. Sometimes faults are put in there because actually the main part, the most interesting part, the best documented part is off to the northwest of where this map is shown right now. But we know we have reasonably good confidence to assume that it comes in through here. So there's, you know, the thing I'm trying to stress here is that always realize that there's an enormous number of assumptions that go into the map that you're looking at on location of various things, whether it's outcrops, whether it's contacts, whether it's faults and other features. They are educated guesses, but nonetheless, they are estimates or guesses. So, you know, keep that in mind. You could easily publish another map of this area and have faults, maybe similar faults, but they're going to be in different locations because.
If it's hidden, you're never gonna go out there and see it.
No, unless you dig a really deep hole, lower yourself down on a rope or something, and I don't recommend that. Yeah, you're basically not going to see it in the tradition that we would see maybe this one right here. Maybe you could go right up there and see that. But we have reason to expect it there.
So,
Yeah.
I don't know if this has anything to do, but you know how it strikes slips and then you get the rock that's crushed?
Mhm.
Remind me, is that Russia?
Yeah, that's breccia.
And would that be along that
Um,
zone, or is that?
Well, there might be some breccia along that fault zone, but it's going to be buried. It's going to be deep,
Right.
and we're not going to see that at the surface.
We should get back to drilling.
Yeah, you might, if you were drilling water wells in the area, you might, you know, go through a rubble zone, think, that's odd.
Yeah, I remember that term
Yeah,
happens.
Yeah, it happens. There you go. Okay. Now, something else I'm trying to stress here is that the amount of complexity that we attribute to a fault is frequently based on how much we can see and how close we look at it. And this is a good example. Okay, the main section right in here along Mineral Point Fault is from an underground mine. It's actually in the Coeur d'Alene area. All right, and you can see that there's a whole number of crosscuts that the miners put in through that mineralized zone through there. And so the geologists, after the mine comes through, geologists are in there mapping surfaces. And so that they can put together a pretty complicated, nice picture of what that fault looks like in detail. And this is pretty good detail. There's on the scale, this first little division here, that's 200 feet. So that's pretty good detail, horizontally and vertically through that system. Now note how St. Elmo and Polaris are represented on that cross section. You think that's what they really look like? No. I suspect they look a lot more like this. But we don't have nearly the information on that. So what am I going to do? I'm just going to probably put in a dashed line and say, well, that's where I think it is. And we all inherently accept that in the business, that, okay, this is somewhere in this area. This I know location is precise. But you can also see how complex most fault zones really are when you get enough data to really be looking at them. San Andreas provides that nicely because it's exposed at the surface, frequently moving, and we can follow lots of little strands of that thing. Other faults are not nearly that well exposed. Okay, another example, this one from map view. Okay, the previous one was cross-section. This is a map view. This is actually part of Yucca Mountain down in southern Nevada, the repository for high-level nuclear wastes that's proposed anyway. Here's my footwall. There's my hanging wall on this side. And yeah, I would describe that kind of as a fault zone going through there. Again, complicated, very complicated. But you throw enough money and enough workers at something like this, and you can get a lot of good information out of it. You can get a sense of what's going on. But again, it's the complexity. You look at this area on like the state geologic map, one line. Okay, but hopefully we all recognize it's not really going to look like that when we get out there. It's going to be a lot more complex than that. Okay. Well, something else, let me just back up here. Something you notice, a lot of these faults are curved, aren't they? They're not straight lines. There's a lot of curvature in these things. So how do you accomplish that? Well, oftentimes what we see is that faults are actually composed of relatively short, straight segments, like I've represented here, both along strike and down dip. You've got these short segments that are joined together by what are called stepovers. Stepovers typically are these shorter little intervals like those two right there. So you have a little stepover going from this segment to this segment, or you can have it down dip and create things like that. But that allows you to create curvature on these faults. Even though a lot of times we represent them as straight lines, that's an idealization. That's not what they really look like, again, if you get into the detail of the thing. Just one of numerous examples. This fault, rather curved sorts of strike in there. So if you measure the strike in one location, what's that telling you? It's telling me in this location, that's what the strike is. Of course, all I got to do is walk over, 50 feet, and I get a different strike. So I can't put all those little strikes on my map, so what do I do? Typically on a map, that would be expressed as one single orientation like that, almost east-west. And then you would approximate what's a reasonable number for a dip amount. I know the dip direction. I just don't know the dip amount. Okay. And to wrap up this segment, what I want to talk about a little bit is our dear Basin and Range Province. Sorry about that. Had a little slug of gin there to sort of keep me going. Okay, basin and range shown by this dark boundary right here. Various people define it different ways, but that's a basic basin and range. Extends into eastern Idaho. The very southeast corner is some good examples of basin and range faulting, but doesn't quite get into our area, not distinctively anyway. But there's a tremendous number of normal faults involved with the basin and range region. Now, the traditional model that was used early part of the 20th century, late part of the 19th century, was that, okay, this is an area of extension where you pull things apart and you develop a whole series of normal faults, creating these so-called Horst and Graben. Okay, good German terms there. The Horst is the high portion, the hill or the mountain. Graben being a lowland, a basin, grave. May have been the original source. Horst and Graben, and students would love it because, well, it's Dr. Pangraben, or something like that. You know, because my name is Panhorst. Okay, so, yeah, oh well. At least they were listening to me. They were awake, that's good. Okay, simple Horst and Graben systems, normal faults. Okay. But that has evolved over quite a period of time to realize, no, that's way too simple. That doesn't explain the basin and range the way it needs to be explained. First of all, one of the things we found are what are called half-graben structures. Half-grabens come because now this normal fault, once it gets deep, say 10 miles, maybe even 15 miles deep, it actually flattens out. It becomes what's called listric, like a shovel. Okay, and it actually flattens like that. And then there's a whole series of other smaller normal faults that all sort of interact with that. So you can actually achieve a much greater amount of extension using this kind of system than your standard high angle normal faults. So that was one feature that helped explain some of that. Let me show you an example of it from Railroad Valley in Nevada. Top panel is the uninterpreted seismic section. Seismic is the system where they basically go out and they shake the earth and have these very sensitive geophones out there listening to how what the shaking's doing and receiving back some of the sound, if you want to call it that, energy that goes down, reflects off something, and comes back up. Okay, now this down here is the interpreted part. And what we see here is that what makes this a half graben is that on the east side, you've got a very large main normal fault, but the west side of this is a whole series of smaller normal faults, making this kind of a lopsided basin. It's not even all the way across. The thickest accumulation of sediment isn't in the center of the basement. It's actually off to one side, which is not an uncommon situation. A lot of people have tried to interpret portions of the western Snake River Plain in this fashion to be able to say, well, this is where we're getting the primary amount of sediment deposited, and so it's telling us about the complexity of the normal faults that are involved in that. Okay, yeah.
How does the two-way time in that refer to the depth? Since two-way time in seconds going down and coming back up, how does that refer, like if you were to run a sat to the depth of how deep that is?
Yeah, well, you have to make assumptions on how fast the energy is traveling through those, and then how fast it's gonna come back to do that. Different materials have different speeds, and so if you make some assumptions and then you try to model that and say, well, does that sort of make sense? You may have to go back in and fiddle things a little bit. Yeah.
Yeah, I think for something like this, you can actually probably calculate each layer pretty directly.
Yeah, okay. We have some geophysicists in the room here, so there's two of them in the back row. That's why they're sitting back there. But yeah, it gets into that. To me, a lot of this is kind of like geomystics, is what I always refer to it as. So I didn't really understand it. I see how useful it is, but it's a lot of it's kind of mysterious to me. But nonetheless, it gives us a way to look deep below us that we really have not had prior to that. You know, back in the 19th century, it didn't have anything like this, so it's very useful that way. Okay, so a more updated interpretation for the formation of the basin and range, all right, would involve, first of all, back in time, 15, 20 million years ago, when we had active subduction going on all along the western side of the United States, you were pushing that North American plate, you know, it's kind of giving it a shove and building up a large pile of rock inboard from the coast. Think of South America nowadays with the Andes Mountains right there. You've got active subduction going on right offshore. It's pushing that continental block, and stuff's kind of packing up. All right. Go forward in time a little bit. As that active subduction zone is then itself, active spreading zone, then is actually subducted, you lose that push, and all of a sudden, that kind of quits. Well, now this big pile of stuff you got here, it's, well, more than subside, it's going to kind of fall apart. Yeah, it's going to start to spread out. It's going to extend. And so you're going to get, in deeper levels, somewhat of a ductile flow down here that allows this thing to just kind of spread out. Of course, you also have a lot of heat underneath here, which domes this thing up. As you lose that heat, it's also going to cool off and therefore subside as well. So you got a lot of stuff going on there at once. But the point is that all of these are interacting to create a situation where you're going to kind of pull that back apart. You can make the prediction. That's what's going to happen in South America far into the future. Same process is going to happen. We're going to start spreading out that large pile of sediment. In fact, some workers down there feel like we've already got evidence of, at least on the eastern side of the Andes, where things are starting to kind of slide off in big scale. Yeah.
Could the passage of the Yellowstone hotspot kind of happening in the general area around the same time accelerate that as well?
Well, of course, it's going to be north of here. You know, if you're talking northern Nevada up into Idaho, closer to us. Yeah, but it could well be part of that same system. And that's where you get into a lot of fistfights and at conventions about, you know, exactly how does that all interact? You know, the hotspot and the subduction activity and the spreading center, et cetera, et cetera, et cetera. So there's a lot of stuff there we really don't understand very well. We can kind of generalize, but we don't have a lot of the real good specifics because everything's deep. We can't see it, and so you just have to work on evidence that you can collect elsewhere. Okay, something else that we know has happened is also more than 10 million years ago, greater than 10 million years ago, the extension direction was sort of northeast to southwest. It was being pulled apart that way. And for reasons that we don't really understand very well, over the last 10 million years, we've had this about 45 degrees clockwise rotation of that extension. And so now it's actually it's sort of extending in that fashion, sort of a northwest, southeast direction. Exactly why it rotated, don't know. But nonetheless, that has been going on. So if you look at a map of the Nevada area over into California, San Francisco over here, Great Salt Lake is that dark blotch up there. Okay, you pull it apart, that's approximately the modern direction of extension. And if you note, there's a lot of similar orientations in the ranges in here, the Horsts, if you want to call them that, because they're responding to what we see at the surface is actually a fairly recent development, relatively speaking, to the whole history of this region. And so those are relatively recent, 10 million years or less phenomenon going on there. Not all of them, but nonetheless, overall, if you're going to generalize, you could make that sort of that connection. Okay, now we're going to start talking about the Western Snake River Plain. Okay, anybody need to get up and do some jumping jacks or something like that? No. Okay, so what I'm going to be doing is working off a diagram. Now, those of you who were here before received a similar looking diagram, but not this exact diagram, because I always change it to suit my evil plans for the day. And this one has been revised. So take a copy, pass it on back, scribble on it, do what you want, make a paper airplane out of it. Put it in your notebook, whatever you want to do with it. It's yours to keep. And I'll be referring to this diagram as we go along. Okay, so that's why it's good to keep it handy. Don't make it into a paper airplane too soon. At least wait till I'm out of the building. Okay, now let me point out a couple things to you. First of all, if you look at the top of the diagram, the far left column where the epochs are, I put those in on there because you hear that terminology frequently. Okay, so now you know the boundaries between the Miocene and the Pliocene. Okay, well, that's at about 5 million, give or take. And those numbers get revised every so often, just little tweaks as we learn more about it. But those are pretty good estimates of the nature of the boundaries in there, plus the designation, early Pliocene or middle Pleistocene. What's that mean? Well, you kind of got a sense of what the time frame is. Now, I purposely laid this diagram out to scale. Okay, so if you look at the far right column, you'll notice there's a whole series of like little boxes going down there. That's because this is chronologically to scale, which you don't frequently get in diagrams like this. But because of the short nature of this diagram, it works for that. Okay, the next big region in the regional geologic activities. I've listed some in there, like Lake Idaho, when the deposition was going on, and a few other features. In general, when there were abundant basalt eruptions ongoing, at least from the geologic record and what's been dated, it looks like we'd call that a time of a lot of eruptions versus times when you don't have as many eruptions. And then the next column over are specific events, in particular we're going to be talking about today. So I'll be referencing those. Many of those, particularly the volcanics, are referenced in there, have a time designation on them in millions of years. That's what's in parentheses underneath that. And that's because they have been radiometrically age dated, and so we've got good control on how old they actually are. Other things we don't have as good control on. One thing you can also see, all those vertical lines in particular, they all sort of are a little bit fuzzy on the ends. And the reason for that is that it's not really clear necessarily when something started, nor is it really clear when something ended. We know that it occurred during this interval, but we can't tie it down any closer than about that. Okay, so there is a reason for presenting it in that fashion. Okay, now let's start first of all with a little bit of sort of a background. So we're going to go back prior to the development of the Western Snake River Plain. Now, I know there's a lot of fine print on here, so you may not be able to read this. But the idea here is we're looking sort of at the basement rocks, what's either at the surface or close to the surface anyway, within this region. We've got the Idaho batholith, which is up in here, Coming across here, there's granite exposed in the Oahes. So it's reasonable to assume that this Idaho batholith also extended across what is now the Snake River Plain back in the day. Okay, that's the oldest rock in the area. That's Cretaceous age, 70 million or something like that. Ages on that. So we've got that represented, plus between about 15 million and maybe 17 million years ago, you had the Columbia River basalts in the process of erupting. And a lot of that stuff flowed down this way. And you can see the examples, make sure I don't stab somebody here. Oh, sorry. Of some CRBs getting into Idaho in this section. We've got over here by Weiser, there's a whole big section of it. And from what we have learned, it appears that we also had Columbia River basalts kind of filling in at least part of the western Snake River Plain back before the plain actually was in existence as we know it today. So it does exist down into this area, and then there's a hodgepodge of other things in here. Also for reference, they put the Bruno Jarbidge Eruption Center on here, and we'll be talking more about that as we go along. So how are we so confident that that's what is really going on in there? Well, if you look at this in some cross-section, here's an example of a cross-section that includes some deep drill holes, okay, in this never-ending pursuit of oil or other water sources in some cases. You drill deep, and this unfortunate well found a plethora of basalt underneath there, which is really good information for people who are interested in the origin of the area, and really bad information for the oil companies. But nonetheless, everything from this sort of stipple pattern down here, all down, we have this Miocene age basalt. Okay, so that's the Columbia River basalt material that flowed into this area. If you continue to drill deeper, it's reasonable to expect that you'd probably eventually hit some granite down there too. But those drill holes are very expensive. Only the US government can afford to drill such drill holes purely for scientific purposes. Okay, now, we got the basalt, and then we've got Lake Idaho sediments on top of that. And we'll get a lot more into that here in a little bit. But something I do want to point out on this cross-section, because we see it on other cross-sections too, you've been exposed to it whether you realize it or not, and that's this nasty little thing over here called vertical exaggeration. So this is not, I can guarantee you, this is not what a cross-section of the Snake River Plain looks like. How do I know that? Because the authors have told me that. They have exaggerated the vertical at the expense of the horizontal. You do that to show the kind of information and the relationships that you want the reader or the user to understand. So how did we come to this? What this means, we'll just call it 10 times vertical exaggeration. Well, look at the distance from here, plus 1 kilometer altitude, to here, -4. Okay? That's 5 kilometer length in a vertical sense. So 5 kilometers this way represents 5 kilometers this way. So that is 10 times the length of that. And if you ever doubt it, pull out your ruler and check the author. I've actually found some errors that way. I like that. It gives my life meaning. That's why I like it. Nonetheless, we'll see this in some of the other cross-sections we're going to be looking at today. It's often what's referred to as the rubber band effect. If you ever take a big rubber band and put a mark on it that's sort of at an angle, and then take it and stretch that rubber band and see what happens to that mark. It stretches and it goes almost vertical. if you stretch it far enough before the rubber band pops. So it's the rubber band effect. So they've even included this exaggerated dip scale. So that here, that's not actually 1 degree there to there. That's actually 10 degrees if you measure it. It's close to 10 degrees. But even that, you get distortions because as you go down this way, it gets more and more distorted. So you get a lot of vertical distortion at the expense of horizontal understanding. That's essentially the reason one would do this. But it gives us a good representation. But you realize that's not what it really looks like. That's one representation that's trying to give us certain information. Okay, everybody clear on that? Vertical exaggeration? Okay. All right. Whoops, pointed it the wrong way. There we go. Whoa, oh, it was just slow. Wake up back there. What's the matter with that thing, Clint? Okay, another representation. This one's from Terry Maley's book. Okay, good book, good reference. The latest one, the 4th edition, showing again a cross-section across the Western Snake River Plain. Okay, I like what he did here. Idaho batholith, question mark? Well, it's reasonable to assume that it might well be like that. And then you have a lot of Idaho batholith down here and more Idaho batholith back up into this area. There's our Columbia River basalts underneath that, to a certain thickness anyway. This is it's a cartoon in a sense, as they're often referred to. Not that it's silly, but it's not intended to be an accurate representation. It's intended to show information. And then you have Lake Idaho sediments on top of that. We have the Bruno Jarbidge over here, the eruptive center. I will ding him on a couple points though, because on the original diagram of this, if you look in the book, it doesn't say magma chamber there. It says batholith. I disagree with that. I don't think that was the batholith. I think that might have been an editing error that actually, that's probably meant to say that's the magma chamber because you've already got batholith right here. Okay, so, but nonetheless, you've got some sort of source for all that rhyolite. It blows out, and the telling information on why this was not a basin at the time this was going on, at least not initially, is because we don't have large accumulations of rhyolite at depth beneath us. We've got basalt and more basalt. Okay, but we don't have large accumulations of rhyolite. Well, if this were a basin, this thing's blowing off, where's it going to go? To the low areas, right? No, there's big piles of ash, volcanic, rhyolitic accumulations out this way, and there's some, in some areas out that way. But in the Western Snake River Plain, they're absent, which workers have decided, okay, that probably means this whole area was a bit of a highland at the time, because it wasn't accumulating this rhyolite. Now, if you go over into the Eastern Snake River Plain and look at those deep drilling over there, oh yeah, you get lots of thick rhyolitic flows there. It was accumulating there, but not where we are here. So it was probably a highland at the time. Okay, now a different interpretation, but nonetheless illustrative, is from the latest roadside geology book, where they also show a cross-section that we're dealing with. A lot of granite down there. Those boys like granite. So they threw in a lot of that. I was also struck how this is almost looking like one of those half-graben sort of structures to it, where you've got this big normal fault here and these other guys over here. Excuse me. But again, right up front, not the vertical scale. Excellent. That's good. Although, can you see the error that they made in their horizontal scale? I think they switched those two. I think that's supposed to be kilometers and that's supposed to be miles. Yeah, oops. Oh, well. Those editors, what can you say? You got to miss it. But a different interpretation, but it captures a lot of the same information. Okay. No rhyolite, or at least insignificant rhyolite there. lots of basalt and a lot of sediment. That's what the authors were attempting to say. Okay, so let's jump on to our diagram. We're starting off down here, Bruno Jarbidge. Eruptive center is going on. Exactly the timing, it's generally considered about maybe 12.5 million years up to maybe 10.5 or 10 million years was the main activity for that. That was going on. Okay, and this is evidenced, at least locally, by a couple features that many of us are familiar with. First of all, like Eagle Rock, right out here. Yeah, you know where Eagle Rock is. We're sitting down here right now, all right? Eagle Rock's, that exposure right out there. You looked at it, whether you realized it or not, probably as you were coming in. You can't miss it. You love it. At least I look at it. That's when I run off the road again. But if you stand down here, okay, and on the edge of the field and look at it, what you see is that we've got the rhyolite right here with some, looks like dikes coming to join it in there. And then the houses are all built on sandstone over there. So that's lake bed sediments up off to the right. But this is obviously much older than the sandstone. I mean, you can't walk up there and say, oh, that's obviously older. No, it's based on the relationship. This one is about 11.8, I believe is what it was dated at. The sandstones, of course, are much younger than that. And then many of you are familiar with Jump Creek, which I talked about last time. Okay, which is southwest of Marsing. How many of y'all have been to Jump Creek out there? Yeah, lots of good rhyolite. Boy, you just love rhyolite. You know, that's good stuff. That's good stuff. You stand out there, up on the ridge, you can see all the rhyolite right in here, and then you've got lake bed sediments out here. And in this case, it appears to be the chalk hills. Lots of sandy sort of siltstones out in that region, and a lot of volcanic ash is also included in that.
There too, right?
I'm sorry?
There's a front right in there too, right?
A front?
Isn't there a fault, sorry?
Oh, a fault. Yeah. Where's the fault? Well, yeah, everybody kind of, well, it's sort of there, right? Well, we don't know exactly where the fault is, okay? It's reasonable to assume, however, it's right along about where this change in slope is from the flat area out here to the steeper slopes over here. So it's obviously concealed. You can't walk out there and see it. But we know that because of the age of this and other relationships, this had to be upthrown relative to this block. And it's relative because, in fact, we know this block's been downthrown relative to here. Whether or not this moved at all doesn't really matter.
So did Jump Creek stay above the lake then?
Probably. Yeah, at the elevation that you're at. You're probably close to the shoreline right now, but you probably didn't quite make it. In fact, if you tool around out there, I don't know if any of you all have gone over to where these siltstones are, and you kind of climb back up this way and go up some of those drainages, you can actually find some siltstone a little bit higher elevation up in there. So you know, well, it got up to this, but all the way up on top, it doesn't look like it ever made that sort of elevation. Okay, where to now? Now, at about 11 million years is the first evidence we have of the large normal faults that began forming the Western Snake River Plain. Prior to that, it doesn't seem like they were active. By this time, it looks like it probably was active. So it is shortly after a lot of that volcanic activity was before that time, but it begins to form. And it appears from the data that's been collected that, in fact, the most active faulting happened during about the first 2 million years. So from about 11 million years when it started, up to about 9 million years was the highest activity for the faults. And after that, they seemed to slow down. And I go, wait, nobody was around. How do you know that? How can you possibly know that? Hence my diagram over here that I'm going to, that is the whole reason I brought this in. Okay, so let's assume we have this situation. Okay, and here's my basin over here, and we'll just call that like that. That side's gone down relative to that side, which has gone up. Okay, let's assume, now I'm going to just make up some numbers here. Believe me, I'm good at making up stuff. Okay, just ask my wife. Let's assume we have a volcanic rock exposed up here in the highlands, which I'll mark in red. All right, and this sucker is, say, 10 million years old. Okay, we age dated it. It's 10 million. Okay, I come out here in the basin and I drill a deep hole. And lo and behold, I find that same unit out here. Okay, 10 million years. All right, and let's say it is 1,000 feet down. All right, 1,000 feet down. Can you all see that? That's kind of light, isn't it? Well, anyway, take my word. Okay, it's 1,000 feet down from here. So it's a reasonable assumption based on the knowledge that we've got from these things that 10 million years ago, this was up here. So now I come over here and it's 1,000 feet below this sediment. Consider this was, you might say, well, actually it was originally here, fine. That's the actual elevation here is greatly exaggerated, purely for the purpose of this demonstration. Okay, so I can say this thing moved 1,000 feet in 10 million years. Okay? A reasonable assumption. Now, there's a second volcanic unit up here. And this one is dated at 5 million years in blue. Okay? Now, if that fault moved uniformly over that whole time, at what depth would you expect to find the 5 million year old flow? At 500 feet, exactly. You would expect to find it at 500 feet. But you don't. It's actually sitting here at only 100 foot depth. So it's right here. And this distance now is 100 feet. So what that tells me is that between 10 million years and 5 million years, that thing moved 900 feet. And between 5 million years and today, it only moved 100 feet.
It's not linear.
Well, no. Well, first of all, it's not a consistent rate of motion to get this. Some faults do seem to show a lot more consistency, but for this, it's not. It's not consistent.
It looks like a growth fault.
Well, it could be. I mean, there's a lot of different ways to interpret this, but you can't deny the fact that early it had lots of motion, later it had less motion. And so this has been done numerous places up in this area, and enough information has been collected that it would appear to be a reasonable assumption that during the first 2 million years from that 9 to 11 interval is when most of the faulting, the side basins, most of that faulting was most active. Now, why is that? Who knows? We don't exactly know how it all interacts. Why would it be then You know, it probably has to do with a lot of the passage of the hotspot on further to the northeast.
Well, the down drop of the plate underneath wasn't uniform either. It was very much jolted and didn't drop
Yeah.
and peel away uniformly.
Yeah.
Because the subduction zone plate did not let go all at once.
No, they never do. So, you know, it's the complications that are built into the system. And there's a lot more complications than what we're able to glean just out of what, you know, information we have today. But nonetheless, that is one thing that's safe to say, that there was a lot of activity in the first couple million years, and then much less activity after that point in time. So we can tie down when the lake for sure was present by this Adape Park basalt, which was dated at 9.5 million years. Because within that basalt layer, the layers that are present in that basalt, there are lake bed sediments. Okay, so it has been captured in a sense. It's got a signature. So we know that Lake Idaho was certainly in existence by 9.5. Prior to that, it might...
You can see cool basalts, they're guilty. You can see how they poured right into the...
Yeah, okay. How far back in time, we don't know. That's a lot iffier. And that's something that people are working on, you know. They want to know, well, can we tie this down? Exactly when the chalk hills, the older unit out there, when did it start depositing? We don't know for sure. But we know by 9.5, it was certainly there. It was present.
The volcanology helps develop the chalk hills in the first place.
Oh, yeah.
So
Yeah, and the Chalk Hills records a lot of ash from ongoing volcanic activity. So you do have that. So, you know, particularly since we had a lot of basalt eruptions going on while the Chalk Hills was accumulating this sediment. So clearly we had a lowland that was collecting all this stuff. Lakes are excellent sediment traps. Anything you throw in them, they tend to hold on to it. You know, they grab it.
they're good record keepers.
Yeah, they're good record keepers.
They don't just blow away.
No, not initially anyway. Okay, so let's take a look at a couple other things that are associated with the Chalk Hills. And this is just a little exercise I want to run through you here to show you, again, give you a sense of what was going on during Chalk Hills time. First of all, at the top there, you've got the Hot Springs limestone, which hosts the algal reef. And probably some of you have been to the algal reef more than once. And that's a really neat exposure. And the other one is this Hot Creek basalt down here, which probably fewer of you have been to. It's a little bit tougher to find, but it's also a very interesting sort of stop in there. I believe Steve was the one that first took us there that one year. Was that 2018 or something like that? No, it wasn't that long ago. Come on. Nonetheless, I'll explain the importance of the Hot Creek here in just a little bit. Baked sediment sounds like something you'd have for breakfast, huh? But no, this is even better. Less nutritious though. Okay, first of all, algal reef down kind of south of Bruno area, Bruno Dunes, isn't too far away. For those of you who haven't been there, this is the location. So we'd be on the south side of Lake Idaho at the time. Nice big exposure of freshwater reef there. Quote unquote fresh water. The water was actually probably kind of alkaline, and it might have been a little nasty to drink, but as what we're used to. But nonetheless, the reefs love it. So there's all kinds of good fossil evidence of the existence of the thing. If you look at it closely, you can see the growth pattern of the segment. And I got a confession at this point. I'm sorry if I'm rambling on, but I got a confession at this point. I was looking at this photo. I've used this photo numerous times in lectures and stuff. And one time it hit me. I looked at that photo and said, that looked like a cow's head, you know? You got eyeball right here, you got the nostril right down here, shaped like a cow's head, and now every time I look at that photo, all I see is a cow's head, you know? Yeah.
And he's got his tongue sticking out.
And he's got a tongue sticking out even. So you can elaborate as much as you want. Yeah, that's all I see, I'm afraid. But nonetheless, let's not diminish the fact that that is part of the algal reef. Okay, baked sediment is only actually like a couple of miles from the... Less than a mile. Well, by road, it was less than a mile, wasn't it? Yeah, down around the corner, kind of. Okay, and that is shown closest to the road by this somewhat inconspicuous looking hill. But this is a very important hill because it's capped with some basalt. This is the Hot Creek basalt. Okay, and you know, down underneath it there's the top cap, of course, there's going to be some basalt there too. And you notice there's this red zone right there. Okay, that's your breakfast right there. That's your baked sediment. Because the basalt rolled on top of the Chalk Hill sediment, it cooked it. That was very hot basalt, and it just cooked the sediment. In fact, I've got one of my favorite pieces of rock. I have, you don't see this too often. Okay, there's the red of the baked sediment and basalt. This is probably a chunk of basalt that fell off the front of the flow or the side of the flow, plopped into sediment.
All the salt was underwater and it went in there.
What's that?
If this was in Alaska, they'd be baked Alaska.
Okay. Now I am getting hungry. Okay, but it's all in one piece. So that's the source of that baked red thing. All right, so now we're going to back up a little bit and take a broader look. So kind of go back almost to the road and look at it. And what do you see? Well, there's basalt there, but there's also a little exposure of basalt out this way that I've been up to. And the perspective is a little misleading. Those are actually kind of almost close to being the same elevation. But nonetheless, that's the basalt, you know, where the baked sediment is underneath, in case you get hungry. And sitting over there, you know what that knob is? That's our algal reef. Now, it's not the site we visited, but it's nonetheless, it is the algal reef right there.
Which way is the online?
It's pretty far off to the northwest from there. Yeah. Okay, so if you look at those two events, and we don't know exactly when either one of those two really occurred, but we can tie it down pretty much. What you're looking at there is a difference of, say, let's approximate it at 2 million years, approximately. A good approximation. 2 million years difference between those two. And if you look back at where we were, there's 150 feet difference between the basalt and the reef. Okay, so that means that 150 feet of chalk hills accumulated in about 2 million years. Okay, so so if you do the simple calculation, that's the quiz. I want you all to do this before you get out of here today. You do the calculation, and that represents about an inch of compacted sediment every 1,000 years. And you think about it, an inch, 1,000 years, that doesn't sound like very much, but that's actually, that's a reasonable rate. That's pretty good. Now, I stress compacted because when sediment gets dumped in the water, it is not compacted. Okay, it's loose, it's got a lot of water all around it, all the pieces do. But as that sediment then is buried deeper and deeper and deeper, it gets squished. And you squeeze the water out of that. You compact it. So what we're looking at here in this calculation is the compacted version, not how much was dumping onto the floor of the lake. It would have been more if you just went out there, you know, waiting and stuck a ruler in it and looking at how much was accumulating. There would have been more. But this is compacted. Okay, but about an inch every 1,000 years. So that was the rate of sedimentation. So that's a reasonable rate. Some places are a lot higher than that. Some places are a lot lower than that. But that's a reasonable rate for a lake of this of this size.
May I ask you, what do we know about the source of the sediment for the chalk hills formation?
Well, it comes from the surrounding highlands. So it's going to be coming from the north side, a lot of the granite that is exposed there, and some of the rhyolites that are exposed. And then from the south side would have had a certain amount of contribution as well.
I was wondering, sometimes when I think about like the presence of like limestones
Mm-hmm.
in sedimentary settings, often their existence points to like an absence of like plastics, and I wondered maybe because the depressions are surrounded by maybe hard weathering rhyolite, maybe that factored into the fact.
The sediment source would have been really important, and I don't think anyone has really worked out exactly where was the reef and where were the streams that were feeding sediment into it. But in general, my understanding of reefs is that they like clear water. I'll put it that way.
They have to have vision in the water, they have to be, they're to have photosynthesis going on.
Well, yeah. So they're going to be close to the surface anyway, so that sunlight can get in there. But also they can't they get choked with too much fine particle material. So there's a lot of stuff there that additionally can be worked out. So we're only beginning to understand a lot of the system.
Flowing into this too?
I'm sorry?
Wasn't the Snake River flowing into this?
Well, some sort of ancient snake river, if you want to call it that, but it didn't look anything like what it does today. It would probably just be another creek coming out of a highland area somewhere. Yeah. Okay. So anyway, during this time interval, okay, starting back about in the 9 to 10 interval, a million years, you had lake bed sediments accumulating as chalk hills, and this lasted up until about between 5 and 6 million years ago. And then for some reason that we don't understand, there seemed to be a hiatus in the existence of the lake, or at least the lake as it was previously. The lake dried up. Well, that's a real simplistic way of saying it. Okay, the lake shrunk. We know that.
It retreated, we don't know why.
We don't know why, and there's a lot of different theories you could put. Possibly the lake was as high as it was because whatever outlet it may have had got blocked by a lava flow, for instance. Finally, the lake got high enough to overtop that lava flow, erode it, and so you were able to drain the lake a bit. You pulled the plug on the tub, and the water goes down. So I mean that's one theory. There's a lot of different things that could have happened that would create a situation where the lake no longer received the same amount of water incoming as outgoing, whether it was through drainage or through evaporation or whatever.
Were the glaciers going on during this time?
No, this is pretty much a pre-glacial, although that's kind of a bad term because you had periodic glaciation going on through a lot of the tertiary. But during this time, it wasn't like what we experienced here just recently, geologically recently. Yeah. So for some reason, it went away. Yeah.
What would it take to prove that little segment that's missing? Or do you have any ideas?
Well, that we know happened because there's plenty of examples where you have the overlying Glens Ferry laying directly on the chalk hills. Directly. I mean, where you put your finger on it. Okay. So we know that has occurred, but what we don't know is how much of the chalk hills was eroded, was removed out of there before that Glens Ferry ever got dumped on top. And that's the kind of stuff you don't know. It'd be hard to really determine that, but people try anyway.
Glenn's very gravel had to be moved by something pretty heavy duty.
Yeah. Well, yeah. So, there's a lot of possibilities as to what caused this. I don't really have a favorite dog in this race, shall we say. So, you know, I'm kind of interested in various different interpretations to see who wins out eventually, if anybody does.
I like that.
You like that analogy? Yeah, okay. Oh, yeah. Okay, so let's move on. So, for some reason, though, the lake started filling back up. Okay, now this is a map, maximum extent of Lake Idaho, generally on the 3 to 4 million year interval is probably when it received this maximum. So, first thing you got to realize, and this is typical of the map, it looks a lot like the one we have out in the museum. Okay, that is a snapshot in time. That is not what the lake looked like 10 million years ago, and it'll look like 2 million years ago. Okay, that is a snapshot in time. But for some reason, after that drying up around 5 to 6 million years ago, we got more water coming in than was leaving. And so the tub started filling back up, okay, and started depositing what we now call the Glens Ferry. And it was depositing upon the eroded surface of the chalk hills. Oh, yeah, yeah. Stuff had been moved out for sure. We know we've lost information. We're just not sure exactly how much information. Well, here's one interesting theory as to why the lake would have come back. Okay, so what we have here is, this is today's situation. You can see Snake River Plain over here, Western Snake River Plain. You can see Yellowstone right here. Well, if you appreciate nothing from Yellowstone, you appreciate the fact it's a high area. Okay, it's up 9,000 foot elevation or more, which means the streams all tend to drain away. These guys are all heading east, going out the Gulf of Mexico. These guys are all heading west, getting to the Pacific. Okay, so Continental Divide, that's part of the Continental Divide. That's the idea. So whenever you're going to have a hotspot, an active hotspot like that, you're going to have this drainage divide. Some streams going one way, some streams going another way. Okay, so that's today's situation. But if we look back in time for Lake Idaho, 6 million years ago, that was not the situation. Okay, where was it 6 million years ago? Well, a typical map of the area, you're going to be back over here somewhere 6 million years ago. That's where the hot spot would be. And if we assume, again, that it's a high area with this drainage splitting both ways, then we had drainages coming out this way, drainages coming back out that way. So that was at about 6, let's say. Just say, for the purpose of presentation here, we're going to say that it probably sat about right in here. That was your drainage divide 6 million years ago. But what about from 6 million years ago up to more present day? All right? This is moving up this way. The drainage divide is migrating up that way. And so all of this area, which 6 million years ago was draining its streams in that direction toward the east, are now going to be reversing themselves and draining it toward the Pacific. So essentially, this area over here gained a significant increase in its drainage basin. So you would be putting a lot more water into this area just by the migration of the hotspot and the migration of that high area. Once the hotspot leaves, what happens? Well, rocks cool off, it tends to collapse, tends to sink. And that's why we get that smile on southern Idaho down there. All right? Okay. So that's one theory as to why we had a resurgence in the lake itself. Nonetheless, starting about in here somewhere and running for up to about 2 million years ago, Lake Idaho was there collecting sediment again, this time what we call the Glens Ferry sediment. Excuse me. And also at that time then, we are going to be developing what eventually wipes out Lake Idaho altogether. And that's the drain that's developing, that will develop in Hell's Canyon. Okay, so another interesting little diagram here that I want to share with you. Let me explain a few things. If anybody needs to leave because I'm babbling too long, take off. You're not going to hurt my feelings.
I'd like to have a copy of that.
I can show you where it is.
I'd like to, know where the copy of that.
Okay. Yeah, no, I can show you right in the, if you've got a copy of the article, it's right in there. So that's what I lifted it from. Okay, you I know, probably have a copy of it already. So we talked about Chalk Hills. The lake was here earlier. For some reason, the lake level dropped significantly to a point where it appeared to almost disappear completely. And then it came back for some reason, which we just talked about, one theory as to why it came back. Peaked out maybe about 4 to 5 million years ago, but then it started this long decline in elevation. The water did. This long decline. They throw some of the evidence for that in here. I'm not going to get into all the details of that. Merely to say that, yeah, that is what was going on. So it developed what's commonly referred to as a spill point. So your bathtub, okay, has this drain at the top, right? And if you get that water up too high, out it goes. That's your spill point. Or your sink has it. Although I've seen a bunch of sinks that don't have it nowadays. I mean, what are they thinking? I don't understand. Yeah, okay. So the spill point that these authors interpret is located exactly right there, and they go through a lot of explanation as to why they think it was right there at the time. So the Snake River now flows down this way and out that way. But the question is, how did that develop? Why there? Well, how did that develop? So to do that, I'm going to use this diagram, but what you're going to have to do, you're going to have to work with me on this, okay? What we're going to do now is just take that away. Just don't think about that spot right there. Okay, pretend that doesn't exist. It's just regular old terrain out there. And
Did the lake have a drain before then?
there's no indication of that.
It's collecting water and
Yeah, the tub was just filling up. Although there's no strong indication that there was. Okay, it may have been. Probably the main drain on the lake was just through sheer evaporation. Because, well, as the lake rises, the surface area expands considerably. Yeah.
this basin is like a salt.
Yeah. It's confined basin. Water level rises, and so you get enhanced evaporation. Okay, so how does that work? Well, if you ignore that being there, what we've got back here now is a situation where you've got a stream back here, but you know what? Lake Idaho's down here. So we're going to go back in time. We're going to put Lake Idaho here. All right. This is just regular old terrain, just, kind of stuff you're going to go out and hike and have a good time. No problem. But that now is not the Snake River. That stream right there. You know what that is? That is an upper tributary of the Salmon River.
It's an ancestral Salmon River.
Yeah, or a tributary of it anyway. Okay, and leading into that now, you've got what's called Rock Creek right here. So it's draining, it's eroding back this way, and it's draining into here. And then over here, we have Hog Creek, which is draining into Lake Idaho. And this is also going to be eroding back a little bit. Little bit every year, every big rainstorm kind of stuff, move a little more sediment down the creek and eventually winds up down here, or on this side, it goes down there, goes to the Pacific Ocean. So they're basically growing closer and closer together. Now what's going to happen when these two actually meet here? You are probably going to have Rock Creek begin to take water and sediment out of Hog Creek. Why? Because the gradient here is higher than it is here. And water always wants to take the shortest route downhill. So it's going to go for the higher gradient rather than the lower gradient. Okay, so it's going to want to drain that way. So it's going to start capturing more and more of Hog Creek until it gets back here and hits the Bonanza. There you got a big bathtub full of water. And that water is going to be pouring down here, a little bit more all the time, erode that out even more, and all of a sudden, it's going to connect in and put a whole bunch of water down that tributary. And it's just going to continue to grow in size. Okay, that is what's happened, only it happened here. All right? Now, I'm going to go out on a limb here, and I'm going to make a prediction for the future that none of us will be alive to see, which is the best kind of prediction. Nobody can prove I'm wrong. Okay. Granted, this location right there, that elevation right there, and that elevation right there are not the same. This one is higher elevation, that one is lower elevation. Why? Because the Snake River is making sure of that, right there. All right? But these two are going to continue to erode the way they are. And that whole process is going to continue. It's going to capture this and then slowly work its way down here. And it works its way back, and pretty soon it's going to meet up with the Snake River. Now, to go from this elevation to this elevation, which way would it want to go? Would it want to go the longer route, or would it want to go the shorter route? The shorter route, higher gradient. Snake River is going to start draining through here. Hell's Canyon is going to be dry. Eventually, you're going to lose most of the flow through there. Okay, Mississippi River does this all the time. Yeah.
Terry, question, where did the salmon and fish come from to get into Lake Idaho? Are any of those fossils, and maybe Coyote knows, are any of those fossils in the Chalk Hills, or are they all in the Glens Ferry?
This one's on you, Coyote.
Well, see, there is a whole bunch of records of the Chalk Hills Formation of ancient fish bones. That's what I like about that spot.
Yeah, there are fish fossils in there, but that wasn't your question.
Well, therefore, if there are fish fossils in the Chalk Hills, there must have been a connection to the ocean before the lake dried up, in a sense, and then reestablished itself and it ended up going out.
And they were landlocked salmon too.
And so there were salmon and fish that were anadromous, and so they were going to the ocean.
Huh?
So there had to be some connection other than just this one that you're talking about.
And the challenge would be, how do you identify that?
Well, the only way you could do that was by the morphology of the fish you're seeing. We have a pretty good detailed fossil record of the fish that's going through there.
Yeah, a lot of that would be based on paleontology, and if you could find some evidence, field evidence of an old drainage system.
So you see, we have some fish, we have snail eaters, and we have other things that prove that lake has been pretty stable for a pretty good long time.
Yeah, so short answer is I don't know, and those are some of the unanswered questions. How does that all work? I mean, how did the fish get into Pyramid Lake, which is extremely landlocked?
But you see, they were ancestral fish. They were there. You ever seen those pupfish in these little holes? Those things have been in there for a long, long, long time.
Yeah.
And so those lakes were active during the Ice Age, and they had routes out. Now all of a sudden they got cut off. You know, one of
Okay.
them- see, there's a whole lot of little.
Whole bunch of stuff.
There was some guy's history that talked about the Snake River went around into Oregon
Yeah.
and hit the Columbia River without even getting close to the Salmon River.
Well, I don't know. I don't know that much about it.
I don't
It's not out of the question, but whether or not it would be, what evidence there is for it, I don't. Well, Okay, back to this diagram. We've got that base level decline, that lowering of the water level in Lake Idaho at the time. Okay, and going at 120 meters per million years. It's like, well, how much is that? Well, calculate that a little bit. That works out to about 4.5 inches of water drop every 1,000 years. Well, in our lifespan, and that's the difference. That's why people have trouble envisioning this, because unless they understand things about geologic time.
The fish and the animals didn't see much either in 1,000 years.
Well, I mean, it's not like they're sitting out there watching it either. So, yeah, but that was the rate. That was the rate of lowering. So it was a relatively gradual process, but nonetheless, it did lower. And if you look at the end of this, we were probably talking about somewhere in the neighborhood of about 2 million years ago. Whether or not it had anything to do with volcanic, the basalt eruptions going on at the time, who knows? But nonetheless, it was going on. One thing you can say that if you look at the full-blown Lake Idaho, if you're going to drain this puppy out, you pull the plug over here, okay, you're going to start draining this thing back this way, and it's going to move in that direction, the shoreline, if you will. Okay, it's going to drain out there as well. And one of the things that people are looking at is, okay, let's look at the sediment, the age of the gravels, essentially, that are coming into this area on top of the Glens Ferry, and can you see that they're actually getting younger as you move in that direction, the age of the gravels? We know there was a lot of gravel during that time at about 1.6, 1.7 million years ago. That's when you had like the 10-mile gravel and various of these other gravels being deposited on top of the lake bed sediments. So we know that the lake wasn't there at that point. It was receding rapidly, probably receding, and these gravels were sort of taken over, moving stuff down. Okay, after that point in time, you haven't seen a tremendous amount of change in this area. So by that point in time, we have this full basin developed over here. Most of the sediment is in place. Yeah, you rearrange the surface a little bit. Humans love to rearrange the surface of the earth. They get in there and do a few things, but by and large, that's all pretty minor stuff. And it just sort of looks like that today. And on that point, I'm going to stop. So, questions? Yes?
So, talking about the valley dropping 1,000 feet.
Okay.
It's awfully incredible to me.
Okay. Well, if you give it enough time.
True, but it happened mostly in the first couple million years, right?
Okay.
But I guess I think about how long it is between earthquakes from basin and range, like the border peak. It only dropped 30 feet
Okay.
at that time. So you're talking about an enormous amount of time, probably an enormous amount of time. Is this typical? Can you point to any other more modern examples about when things drop at a comparable rate that we would recognize or know about?
I think there's a number of faults. The Wasatch Fault down in Utah.
The Lake Bonneville is a good.
Yeah, there's some in that area. I'm familiar with some further east from there. That's not an unusual, over that period of time, having thousands of feet of displacement. When you're talking millions of years, that's not an unusual situation for these kinds of things.
They're sitting out there it's where the Devil's Golf Course is now, but Lake Bahonton is another one.
Yeah. So that's not an unusual event by any means.
Death Valley dropped a long ways too.
Death Valley is a good one. Yeah, that's a good graben area in there that you've got. Most of the large continental basins that you see along that would have rates probably at least in the ballpark of that, kind of similar sorts of events. And if you tie them down to individual faults, you've got individual fault zones anyway, moving at about that rate.
Well, see, Lake Lahontan's got artifacts on one of their terraces as Lake Lahontan.
Okay, so you can do that. Just keep in mind, tectonics is a lot faster than erosion.
Yeah, it is.
If it weren't for that, you wouldn't see mountains.
Show you.
Okay, so it's you know, the fact we have so much relief in areas of the continents testifies to the fact that stuff is moving vertically, generally because of horizontal movement, but it's moving vertically much faster than we can erode it away.
They want you to-
Jerry,
Yeah.
if you look at the basin and range to the north of the Snake River Plain.
You mean out in this area here?
And sort of I've had the theory that somehow the batholith prevented progression of basin and range across our area, that then it diverted the faulting into the Boise front and the Hawaii front, faulted that way instead of continuing
In our area, if you want to call it that.
the batholith.
In other words, it didn't continue in here because you had stuff going on here, but in fact what it did is it was coming up this way and kind of went more over here, is what you're saying.
I'm saying, yeah, that the batholith had some sort of a diversionary factor.
Well, it certainly would influence it to a certain degree, but keep in mind too, with the basin and range, what we're talking about here is a fair amount of kind of superficial sort of failures in the rock, whereas the hot spot, the batholith, you know, whatever terms you use for it down in here, deeper, that's a lot deeper than that. Now, is one going to influence the other? Probably. What's the amount of influence? Lots of speculation on that.
Quite minimal, actually, if you look at it.
Well, that's one theory. Others think there's a real strong influence on determining the faulting versus where the batholith is going to occur. Shirley, you look really anxious to do something.
I'm gonna take a pic when you're, I don't wanna rush you.
Oh, okay.
Nobody moved till I get up there.
She doesn't want to rush, but she wants to threaten. You better not move. Okay. Any other questions?
I'm curious, so I don't know much yet about the geology of the region. I was wondering, was there a lot of ashfall associated with like the volcanic eruptions like around 2 million years? And so is there the potential for good like age constraints?
There are a lot of volcanic activity going on that one could use for age dating. Not all of it is suitable for age dating, particularly ash falls, because they tend to get contaminated so well. But flows work really nicely. And we have such a plethora of basalt flows over that period of time that not all of them have been dated. And so you can work out a stratigraphy, and some of the literature out there is just like, whoa, these guys went out and age dated a bunch and then looked back over all the other things, and they have these really complicated chronologies. It's amazing that what you can do with that. So there is a lot of potential to really nail down the events in chronological order much better.
I guess maybe a slightly related question. I don't know really the details of the chalk hills versus the Glens Ferry, but differences between those, does that speak to some of the changes that are happening through the lifetime of like the Lake Idaho?
My impression is that, for instance, there's a lot more ash layers contained within the chalk hills than there is within the Glens Ferry.
If you look at the interstices in the Glens Ferry, if you really look at it, it's quite a fast deposition. There's
Okay.
no ash in it. I looked at it, it was sandy.
Yeah.
Ash.
Yeah. Your problem is, where are you relative to the source of the ash, and where are you relative to the shoreline? Because if it's really sandy, that suggests you're probably somewhat close to the shoreline, like we have out here with that delta, or Table Rock area where it's dumping all that sand. That's rapid accumulation of stuff. That'd be a lot different than the rate of accumulation and what gets accumulated out in the middle of the lake. So you got to factor all of those types of variables in there as well.
This probably sounds pretty far out, but I'm just curious, Terry. I'm also having a tough time as to why the valley dropped that much. The Basin range down in Nevada, the mountains are generally more to the northeast. The Basin range up in Idaho is generally more to the northwest. So one's pulling this way, one's pulling that way. Is it possible to be some rift effect aiding the drop of the valley?
Well, certainly you would have some sort of rifting effect, probably just because you've got the hot spot down here at about the same time. And so I know geophysically, what's underneath here doesn't quite match, just standard, well, we got granite and we got a little bit of basalt and sediments and stuff. It looks like there was actually a huge amount of basalt underneath there that injected possibly along some zones of weakness within there, which would, but that would be at the time that all of this occurred. Then this moves on. This is going to kind of cool off a little bit, subside, etc. And so you get effects on
The
that.
whole continent's rotating. People keep forgetting that.
Yeah, well, yeah. You've also got a certain element of North American plate rotation built in. So it's well, yeah. Yes.
Yeah, way back at the very beginning, you had shown the Columbia River basalts lying directly on top of the basement rock. I mean, is that do we actually think that's what it looks like there, or
Yeah.
do we just not know?
Well, part of it is a certain lack of knowledge, which never stops a certain lack of speculation. Okay, but yeah, I think there is evidence that you've got in places basalt resting directly on the granite. Okay, so that gives us an idea that this was exposed at the surface at the time that Columbia River basalts were poured into this area. Yeah. Okay, well, on that note, it's almost 3 o'clock. I'm sorry I took that long, but